Good morning, everyone. Today we're starting one of the most fundamental concepts in all of calculus, that's the limits. Now, some of you might be asking, what does it mean, limits? But here's the thing, you've been actually using the idea of limits your whole life without even realizing that. Think about this. When you're driving and approaching a red light, you gradually slow down as you get closer and closer to the stop line, right? You're essentially approaching a stopping point. That's the intuitive idea behind limits. So today we're going to make this more mathematical. But before we dive into limits, let's warm up with something you already know, lines and slopes. Okay, so let's start with the basics of the equation of a line. The slope-intercept form is y equals to mx plus b, right? Where m is your slope and b is your y-intercept, right? Now, what exactly is the slope? It's the rate of change, how much y changes when x changes. So let's say if you have 2 points, x1 and y1, and x2 and y2, right? So the slope between these 2 points will be m equals to y2 minus y1 divided by x2 minus x1, or we also call it rise over run, right? So let me walk you through a quick example. If we have points, let's say 1, 3 and 4, 9, what would be the slope? So the slope is, so let's say this is my x1, y1. This is my x2, y2. Then we have, by this formula, we have 9 minus 3 over 4 minus 1, which is 6 over 3, which gives us 2. So graphically, what we have here is these 2 points, and we connect them with a line, right? And now we say that every unit we move to the right, we go up 2 units, right? And then again, 1 unit to the right, 2 units up, 1 unit, 2 units, right? So we essentially are moving like this. So that's pretty straightforward. Thus, slope is really just a rate of change, how much y changes when x changes. Now let us connect this idea of slope to curves. If we have a curve, not a straight line, we can still pick 2 points on it and connect them. The line through those 2 points is called a secant line. So the formula for the secant line is the following: f of x 2 minus f of x1 over x2 minus x1. Notice that this is the same formula for slope, but now the points come from a curve y equals to f of x. So let's look at the example. So let's say we have some random curve, something like this, and then we pick 2 points on this curve. So this one will have the coordinates x1, and that is my y, or f of x1, right? So y1. And for this one, I have x2, and the y coordinate will be f of x2, right? So this is where this formula is coming from. It's the same thing as we had before. M equals to y2 minus y1 over x2 minus x1. But now instead of y2 and y1, we have f of x2 and f of x1, right? So the same thing. So now to find the secant line, or line that goes through both of these points, this is going to be the slope. We don't really need to find the secant line per se. We just need to find the rate, right? So the rate of change, or the slope of this secant line. So as an example, we have the following. Suppose a ball's position in meters after t seconds is given by the following function. S of t equals to 5t minus t squared on the interval from 0 to 2.5. So this would be imitating the physical scenario where we just roll a ball on some flat surface, right? So we have some kind of ball on a flat surface, like let's say bowling ball, right? And we just push it and it starts moving. It moves at the beginning fast, and then as it goes further, it kind of slows down until it reaches its natural stop, right? And this is where it stops. Okay, so this would be imitating this scenario. So this is how the graph of the position function S of t looks like, but since we are working only with the interval from 0 to 2.5, right? We'll be looking only at this portion. We don't really need this portion. So what it means is essentially what this model says is, let's say if we were throwing the ball up, and it will just go up, and then it will stop for a second somewhere on top, and then it will go back, increasing its speed, right? And then it reaches the bottom. So this is essentially the what it mimics. But in this case, so this will be where we throw the ball, and then it moves up. It kind of like here where it reaches its maximum and stops for a second. So its velocity is 0 at this point, and then it starts moving back down as time goes on. We are kind of starting with this lower velocity, and then the velocity increases as we're reaching closer and closer to the ground. This is not the trajectory, okay? We're not throwing a ball this way and it's just like we're just throwing it up, and then it stops for a second and then goes down. But for our case, we have a bowling ball, right, that we just kind of send on a horizontal flat floor, and we give it a push. So at first the velocity will be high, and then as it moves on, it naturally stops, right? So this is where it will eventually stop. So we don't really need the second half of our parabola. So let me just erase that. Okay, so this is what we have. So when time is t, again, this is my t-axis, this is my s of t, right? This is my position function. So this model says at the start t equals to 0, the ball is at the origin and moving forward quickly. As time passes, right, the ball slows down, and at t equals to 2.5, this is where the ball stops moving forward, right? So this is a graph of s of t. This is a parabola that rises, and then it kind of flattens out if we were to continue, because the ball continues staying and not moving anywhere, right? So let's find the average velocity of our ball at some points, right? So velocity is the slope of the position function, but at first, we can only measure average velocity over a time interval. So the formula is the same as for the slope, right? It's just we are changing the notation a little bit. So we have velocity, average velocity is s of t2 minus s of t1 over t2 minus t1. This is nothing more than a slope of a secant line between 2 points, t1, s of t1, and t2 s of t2, right? So for example, let's find the velocity between t equals to 1 second and t equals to 2 seconds. On the graph, it's gonna be from here, actually right here, t is 1 second and t2 is 2 seconds, probably somewhere here. So we are essentially looking for a slope of this tangent line. What do we use? As before, V average is, so the function was s of t was 5t minus t squared. We have 5 times 2 minus 2 squared. This is my s of t2 minus 5 of 1 times 1 minus 1 squared. This is my s of t1 divided by 2 minus 1. This is my t2. This is my t1. And what I get is 6 minus 4 divided by 2 minus 1. That's 1. So I have 2 miles per second. That means that the ball's average velocity during the 1 second window was 2 meters per second. Now, but average velocity is not the same as the ball's actual speed at exactly t equals to 1, right? At that moment, the ball has a single instantaneous velocity. So how do we find it? We look at smaller and smaller intervals around t equals to 1. Okay, so remember the formula. T average is s of t minus s of 1 over t minus 1. So let's try a few values of t that is close to 1. So let's say when t equals to 1 half, then the average velocity will be s of 1 half minus s of 1 divided by 1 half minus 1. So we would end up, so what you need to do is you need to plug in the values, the 1.5 into the function. Remember, the function was s of t is 5t minus t squared, right? So you'll have 5 times 1 over 5 minus 1, 1.5 squared. So this is your s of 1.5, and then minus 5 times 1 minus 1 squared. This is your s of 1. That's all divided by 1.5 minus 1. So you'll have approximately 2.5 meters per second. Okay, now what if we take a closer, so graphically it looks like this. So we have, okay, so a point right here, and then 1.5 is gonna be a point right here. So if I zoom it in, I have a secant line like this. Yes, like this. Before, as you remember, we had t equals to 1, right? So that's going to be this point. And then t equals to 2, that's going to be this point right here. And we were drawing the instantaneous, sorry, the secant line through these 2 points. It's kind of hard to draw it. Let me grab another color. Like this, right? So you see your slope from 1 to 2 was lower or smaller than the slope of a secant line from 1 to 1/2, right? So it's getting more kind of steeper and steeper. So if we get a smaller value, let's say something like 1.1, right? And find, so it's probably somewhere here. Let me erase this one. And then find the slope of a secant line that goes through these 2 points. You see it's going to be even steeper than the previous one, right? So now let's look at this mathematically. So we have for T1 equals to 1 and T2 equals to 1.1, we will have average velocity will be approximately, so we have S of 1.1 minus S of 1 divided by 1.1 minus 1, so we will have approximately 2.9. And then if we take another point that is even closer, let's say T1 is 1 and T2 is 1.01, right? So we'll have average velocity S of 1.01 minus S of 1 would be divided by 1.01 minus 1. We would approximately have 2.98. So as you can see, we're approaching value of 3, right? So the instantaneous velocity at time 1 second, right, is 3 meters per second approximately, right? So again, to reiterate, when we have 2 points, okay, so we have 2 points, one is T1, another one is T2. When we draw a secant line, the slope is this one, right? So let me draw a line. So this is my first slope, or V average, for these two, between these 2 points. Now, if I move closer to T1, so let's say I have this T3, right? So then a point will be right here. So if I draw another secant line through these 2 points, this is my V average. So let me mark this as T1, T2, and this is my V average between T1 and T3, right? As you can see, it's much steeper than the first one, so the velocity is increasing in this case, right? So, and then if I move even closer to T1, let's say I'm somewhere like right here. So that's my T4, and the point on the graph would be here. And then if I draw a secant line through this 2 points, I have my velocity between T1 and T4. As you can see, the slope of this secant line is getting bigger and bigger, right? As I move closer and closer to T1, it's gonna be even steeper and steeper, so that it just, as we move closer, we are essentially reaching this line that is just touching our curve. So this is where we get to the instantaneous velocity. So average velocity is not the same as the ball's actual speed at exactly t equals to 1 second. At that moment, the ball has a single instantaneous velocity. And how do we find that? So this is where we connect the back to the slopes of the lines. So a tangent line is the line that just touches a curve at a single point and has the same slope as the curve at that point. So as we saw before, our secant line moves closer and closer. So eventually we will have just this tangent line, right? That is just touching my graph, at this point T1, it just touches here. So the slope of this tangent line is exactly the same as the slope of my curve at that specific point, T1 equals to 1 second for our previous example. So how do we find the slope? By taking the limit of the slope of secant line as the second point gets closer and closer to the first. So let's go back to our previous example. We had t equals to 1. So m10, which is the slope of the tangent line, would be limit as t goes to 1 of s of t minus s of 1 divided by t minus 1. So when we plug it into the into here, we get undefined. But if we look at the points that are very, very close to this one, we are essentially approaching the value of 3 as we saw before, right? So that means that the tangent line to the curve at 1 comma 4, right? That was the previous, the original example. The slope of this tangent line is equal to 3. And the equation of this tangent line would be y minus 4 equals to 3 times t minus 1. Y equals to 3t minus 3 plus 4. So we have y equals to 3t plus 1. So this would be the equation of the tangent line for the example that we had with our rolling ball with the function s of t equals to 5t minus t squared at time 1 second. So the intuitive definition of a limit, we noticed that we couldn't compute the velocity at a single instant directly, but instead we computed the average velocities over intervals that shrank smaller and smaller. These values approach a single number 3 in our example. So we say a limit is a value that a function approaches as the input approaches some number. And in our case, it was limit as t approaches 1 of s of t minus s of 1 over t minus 1. It was equal to 3. So that's the power of the limits. Next, we will formalize what the limit really means and learn rules for computing them.